Greetings, Panthers. Dr. Augustine today. Hope you're doing well. Recording on this icy day, so you don't get to have me in class, but we get to just go over a few of the last remaining topics in chapter 15. And one of the topics we're going to talk about is the effect of catalysts and surface area on a reaction rate. So remember we said there are four things that influence the reaction rate: the concentration of reactants, temperature of the reactants, presence of a catalyst, and surface area of solids or liquids or of the catalyst. So just quickly recapping, we had this thing that we called a rate law. Rate was equal to K times the concentration of some species A raised to the X power, some species B raised to the Y power, some species C raised to the Z power, et cetera, et cetera, et cetera. Depends on how many things you have. And if you look at that equation and you look at the information you have, this information right here is the concentration dependence, the A, B, C, plus all the orders of those reactions. And then all three of these things are buried in K somehow. Okay, so inside of that rate constant is the temperature dependence, whether there's a catalyst, and the surface area. Now you also recall that K was given by the what's called the Arrhenius equation. K is equal to this pre-exponential factor A, E raised to the minus EA over RT. Remember, EA is called the activation energy. R is called the ideal gas constant. I'll just write these down. EA is activation energy. R is called the ideal gas constant. And T is the temperature. And this is the temperature in Kelvin. It's the absolute temperature. And also recall that the ideal gas constant, this is not the one we learned back in the gas laws chapter. It's 8.314 joules per Kelvin mole. Those are the units on the ideal gas constant. Strangely enough, the other one was 0.0821 liter atmospheres per Kelvin mole. So you might not realize this, but a liter atmosphere is actually a unit of joules. So if you convert liter atmospheres to joules, you get this equation. So this is a super important equation. We already did some stuff with this last time. We talked about the effect of temperature, and we also said that because temperature is in the exponential, a very small temperature change results in a large change in the rate. We also said, just as a sort of ballpark number, that if you have a 10 degrees C increase in temperature for a typical reaction, you get about a doubling of the rate. All right, so that's obviously the temperature dependence. That T in there in the exponential is the temperature dependence of the reaction rate. Now we got the presence of a catalyst or surface area, and that's either going to be in this pre-exponential or it's going to be in the activation energy. And the place where it probably occurs most frequently is in the activation energy. So let's just sort of sketch out what that is, just so you remember. We would have energy on this axis, and we would have, they call this the reaction path. Okay, and let's suppose we have an exothermic reaction. This might be our reactants here. This might be our products here. You may have wondered last semester, what's in between those two things? Well, what's in between those two things is the activation energy. That's the hill that prevents the reactants from spontaneously converting into products. And this height, whatever the height of this is EA. And just a couple other notes. This might be delta H here. And in this case, this would be an exothermic process. Reactants goes to products. Delta H is a negative number, which tells us that this is exothermic, right? So start here on the reactant side, go to the product side. Delta H is a negative value. It is exothermic. Someone asked me a question after class. What about going in the reverse reaction? What if we were to go from product side to the reactant side? Well, in that case, the activation energy is actually equal to the original activation energy plus delta H. So it's a much bigger barrier to go back. So the question they asked specifically was, if this is an equilibrium process, does it readily want to go back? Because I had showed an example with an equilibrium process. And the answer is, in this case, if it's exothermic in the forward reaction, it's going to be pretty unfavorable to go back in the reverse reaction because first of all, you have to climb the delta H hill. That's got to be positive delta H. And then you have to also add the activation energy in. So the new activation energy for the reverse reaction, so we'll call this EA1, EA2 would actually be equal to delta H plus EA1. Okay? So that gives you a sense or gives you an understanding of this idea of an activation energy. It's basically the hill you have to climb over to get over to the other side. All right, so how does a catalyst work? Well, a catalyst works in two different ways. It can either influence the pre-exponential factor, either influence A, or it can influence E sub A. And how does it influence the E sub A? What it does is it might effectively lower this activation barrier. And it may give you a couple different steps. We just talked about in that in the video, the prior video about multi-step reaction. So it may drop the activation barrier. So now we only have to get over this first hill. This might be the rate limiting step. Once we get over that first hill, then it's going to rapidly go down to the product side. Now, because EA is in the exponential, e to the minus EA, a small change in activation energy is going to result in a large change in K. Just like a small change in temperature results in a large change in K. So if we drop this thing by 50%, we're going to have a huge increase in the rate. All right, so let's talk a little bit more about what the heck a catalyst is. I haven't even really defined what a catalyst is. A catalyst is a species which speeds up a reaction for the reasons we just mentioned. And by the way, we just said that the reaction could be activation energy. It could also be this factor. It could lock a reactant into a certain position. And remember, one of the factors in A is the orientation factor. So it could impact this, or it could impact the activation energy, or both. Either one's going to speed the reaction up. All right. So what is a catalyst? A catalyst is a species that does not get used up, but speeds the reaction. We have two different types of catalysts. We have one that's called a homogeneous catalyst and one that's called a heterogeneous catalyst. By homogeneous catalyst, what we mean is both of them are in the same phase. So if the reaction was a liquid and the catalyst was a liquid, that would be an example of a homogeneous. If it's a gas, if there's two gas phase, that would be homogeneous. So I'm going to give an example here of a homogeneous catalyst, and another example would be enzymes would be a good example of a homogeneous catalyst, biological system. Heterogeneous catalyst means the catalyst and whatever the reaction is are not the same species. So you could have a solid catalyst for a gas phase or liquid phase reaction. That would be an example of a heterogeneous catalyst. So let's take a look at a decomposition reaction, which is a catalytic reaction. So the example would be the decomposition of hydrogen peroxide. So H2O2, which is a liquid, will decompose spontaneously into water and oxygen. And if you have a bottle of hydrogen peroxide in your closet and you leave it sitting there for months and months and months, it'll eventually break down into just water, and some oxygen gas will form in there as well. And you no longer have hydrogen peroxide. But that's a very slow reaction. If you just leave it in the bottle, the reason why they leave it in a dark bottle is because it's light sensitive and it will slowly degrade. But we can speed the reaction up considerably by adding bromide ions. So if we add bromide ions, this is the actual decomposition reaction then. 2Br minus plus H2O2 in an acidic solution plus H plus, 2H plus, yields bromine dissolved in water plus water. All right, so this first reaction is the first step in this decomposition reaction. Now you notice the H2O2 is turning into water. However, you might be wondering, well, wait a minute. I thought you said the definition of a catalyst is you don't use up the reactant. So these two bromide ions are being converted into bromine, molecular bromine. And so you might be wondering, well, I thought you said that it doesn't change. It only speeds up the reaction. So if this was the only thing that was happening, that would be true. It would not be a catalyst. However, a second reaction also occurs at the same time. And the second reaction is Br2, molecular bromine, also reacts with hydrogen peroxide to reform the bromide ion plus H plus O2. All right, so now if we take a look at these two reactions, we can notice that we've got 2Br minus on each side, 2H plus on each side of the equation, and the bromines are also on the opposite sides of the equation. And I don't quite have this equation balanced. I need a 2 out front here and a 2 out front here. So now I get the reaction I was interested in, the decomposition of hydrogen peroxide to form water plus oxygen. Using bromide ions, it actually reproduces itself in a 2-step process. So this becomes a very fast reaction compared to just leaving it in the bottle and watching it decompose. Now let's take a look at a heterogeneous process. And this one's really common. This is one you're very familiar with, although you may not be aware you're familiar with it. And this is what's called the catalytic converter. So the catalytic converter is inside of every automobile, I should say every gasoline-powered automobile. Electric vehicles would not have this. So out of your engine, remember that's a combustion reaction, so you're burning gasoline and you are forming CO2 plus water. Except out of the actual reaction, it does not completely react. You don't get all CO2 and all water. Some of the stuff does not react completely. So you end up with carbon monoxide. You have some oxygen in there because you're burning that. You have a bunch of nitrous oxide species. They call these NOx species. On here it just says NO, but there's other suboxides. So we have nitrogen oxide, O2, O3, etc. All that stuff comes out of the exhaust pipe. Neither carbon monoxide nor these NOx species are good for the environment. So the catalytic converter is designed to break down these species which are particularly bad for your health. Now, you also know that CO2 isn't great for the atmosphere, but it's not dangerous to somebody sitting in a garage with the car running. So what's going on? The catalyst inside a catalytic converter is actually a platinum rhodium alloy. It's actually a ceramic. If you ever look inside of one of these or look up a picture of this, it's a ceramic material that has little particles of platinum and rhodium on them. And the platinum rhodium particles have 2 different functions. The platinum part of the catalyst is designed specifically to convert this carbon monoxide into carbon dioxide, and it's also to take the excess hydrocarbons and to turn them into CO2 plus water. So the general reactions are something like this: 2CO gas plus oxygen gas yields 2CO2 gas. That's one of the reactions. And another would be something like this, C6H6. This would just means some hydrocarbon plus O2 gas yields 6CO2 plus 3 waters, often liquid. And so this you'll probably recognize, this is just a general combustion reaction. So the platinum actually helps the combustion process. Catalytic converter gets very hot. There's a high temperature process. And at a high temperature, this reaction occurs quite readily. If you've ever seen the water dripping out of the tailpipe of your car coming out of here, that's from this reaction as well as the overall combustion reaction of the gasoline. So if you have unreacted hydrocarbons from the engine itself, the catalytic converter will help react the rest of those. And if you have carbon monoxide, the catalytic converter, the platinum part of the catalytic converter, will convert that into carbon dioxide. And the rhodium part of the catalytic converter is designed to break down the nitrogen species. So we have reactions like this: 2NO gas yields N2 gas plus O2 gas. Nitrogen is a much safer thing to be coming out of the tailpipe, and oxygen obviously is not a problem compared to these poisonous NO species. So these NOx species will get converted into nitrogen and oxygen when they come out of the catalytic converter. Just a couple of notes about the catalytic converter. First of all, these reactions don't work terribly efficiently at room temperature or cold temperatures. So when you first turn the automobile on, a lot of the exhaust gas gets past the catalytic converter because it hasn't warmed up yet. So early on, when you first run your car, most of the junk that comes out of the tailpipe, the bad stuff, is right when you first start your car up. Once your car's been running a while and this catalytic converter gets hot, these reactions get much more efficient, and therefore it cleans up the exhaust gases much more efficiently. Another fun fact, platinum and rhodium are both pretty rare metals. I mean, you're probably aware these are very expensive metals. 35% of the world's platinum is used in automobile catalytic converters, and 73% of the world's rhodium are used in catalytic converters, which is kind of a crazy thing when you think about how much of these precious rare metals there are go into automobiles. And that's another reason why when a car ends up in a junkyard, the catalytic converter is one of the first things that they get, because they want to recycle that platinum and rhodium. It's pretty hard to find. So you might be asking yourself, well, how does this process actually happen? I mean, why does a solid heterogeneous catalyst, why do these solid platinum and rhodium, why do they actually help? And here's sort of an illustration. This is showing a little bit different reaction, but it gives you an idea of what's happening. I'll just write down what that other reaction is. So this is something like C2H4 gas plus hydrogen gas yields C2H6. All right, so this is called ethylene, C2H4. This is called ethane. We're hydrogenating it. We're adding hydrogen to it. You notice in none of these reactions, in this reaction, you don't see any sort of platinum in it anywhere. Sometimes you'll see it written like platinum, nickel. Sometimes you'll see the catalyst written over top of the arrow, which sort of tells you what they're doing. So this particular reaction, this conversion of ethene to ethane, sometimes you'll see this platinum or nickel or sort of common, or palladium. Those are common catalysts. So sometimes you'll see those written over the arrow. So the way this works is you have a solid metal, and then let's just pretend this is platinum. They have some sort of crystal structure. That's why the atoms are all arranged nicely. And the ethene is in the gas phase. It comes along, and it has some attractive forces to the surface, believe it or not, and will kind of stick to the surface. Now, when I say stick, it's not really sticking strongly. It's kind of on the surface but can still move around. So on the surface but still moving around, this is called adsorption. It's not absorption, it's called adsorption. So the molecule adsorbs to the surface and then can kind of bounce from site to site. The bouncing from site to site is called diffusion. Okay, so ethene comes along, hits the surface, bounces along the surface, and hydrogen comes along, hits the surface, bounces along the surface. It also can diffuse. So both the hydrogen and the ethane can bounce along the surface. Now, what that's doing essentially is it's helping this prefactor term, it's helping this exponential prefactor, it's helping that term with the orientation effect. It basically puts the molecule in the right orientation, and then when a hydrogen finds it, it can react with it. So we get adsorption first, then we get diffusion of the gas molecules along these adsorbed gas molecules along the surface. They'll find each other and react, and then boom, they'll pop off and desorb. So adsorption is grabbing onto the surface, desorption is leaving the surface. And I don't want you to think that the second this thing reacts, it's going to desorb. This is an equilibrium process. Some of these will pop on, some of these will pop off. But what this is enabling to happen is the probability that these gas molecules will find each other in the correct orientation, and then they'll be able to pop off and desorb, which will be this reaction. So the platinum and the nickel speed this process up considerably, because if you were relying on the gas phase, they'd have to hit each other exactly right with the right energy, right orientation, and that process would not be nearly as favorable. All right, so those are two examples of heterogeneous catalysts. Now, let's look at a little bit more in depth at catalysts, and I'm going to mention nanomaterials. Nanomaterials are an important source of catalytics because we have an interesting phenomenon when we have nanomaterials. This is not showing catalysts, this is just showing the effect of size on light emission from a series of different materials. These are actually cadmium sulfide, cadmium selenide nanocrystals. And the weird thing about these is these are the exact same material, but they glow very differently depending on the size of the particle. In fact, the smaller the particle is, the more blue shifted it gets. And this is a quantum effect. It's called quantum confinement. Don't have time to get into that here, but the idea basically is when you have things at the nano scale, things start happening a little bit differently. So this is just a table of some calculation that I did, and let me just show you what this is. If we have a cube that's 1 centimeter cubed, so that means 1 centimeter by 1 centimeter by 1 centimeter. This is the same thing in meters instead of in centimeters, micrometers, nanometers. So the length would be 10 to the minus 2 meters by 10 to the minus 2 meters by 10 to the minus 2 meters. In a 1 centimeter cubed cubic structure, the volume would be 1 times 10 to the minus 6. The surface area, you would take basically, you'd figure out what the area of each face of the cube is. And in a cube, you have 6 faces, 1, 2, 3, 4, 5, 6. You have one on the top, one on the bottom, 1, 2, 3, 4, 5, 6. So you have 6 faces. So whatever the volume is, you have that times 4. So you take 1 centimeter or 1 centimeter times 6. That gives you the surface area. And so the surface to volume ratio would be the surface area divided by the volume. All right, so for a 1 centimeter cubed object, we have a surface to volume of 600 per meter. All right, so this ratio is important in the catalytic process because if you think about what's happening here, all of this action is happening because of the surface. So if we can increase the surface relative to the volume, we can get much, much higher catalytic activity because we have much more surface area. So I'm not going to walk you through every single line on this table, but let's just go to 1 nanometer. So we start with 1 centimeter, and then let's pretend we were to somehow break this. If we were to take this 1 centimeter and we were to make nanometer long cubes in all directions, of course, I'm not drawing the correct number here. There's hundreds of millions actually along each direction. But if I was to divide this 1 centimeter cube up into 1 nanometer cube sections, so we'd have something like this. Each one's a nanometer, 10 to the minus 9. That's the length. 10 to the minus 9 times 10 to the minus 9 times 10 to the minus 9. The number of particles would now be, instead of 1, we would have 10 to the 21. And the volume would still be exactly the same. So we'd have the exact same volume, except now the surface area would go from 6 times 10 to the minus 4 to 6 times 10 to the plus 3. And the surface to volume ratio would go from 600 per meter to 6 billion per meter, 6 times 10 to the 9. So we end up with a massive surface to volume ratio. So there's actually a lot of research right now on catalysts using nanomaterials because we get much, 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 much more surface area compared to volume. So in other words, if you think about if you're trying to understand what I'm saying here is only the atoms at the surface matter. So if we have a bunch of atoms on the inside, and let's say here's